Hello everyone, so for today's lecture, our topic would be about moment of inertia. So let's define the term first. So when you are to Google the term inertia, you would stumble across this definition right here by Oxford. So according to Oxford, inertia is a tendency to do nothing or to remain unchanged. And if you are to look at this definition right here very closely, it is very synonymous to the term resistance. So that is for inertia in a nutshell. But what about moment? So in physics, when you hear the word moment, the first things that you would think of are the units. Let's say Newton meter, Newton millimeter, kilonewton meter, let's say pound foot, pound inch, and etc. So basically, your moment is an expression involving the product of a certain force and its perpendicular distance about a certain point. So for example, that this is to be your point. For example, that this is to be your force, I should say. And let's say that you are to analyze this point right here. If you are to measure this distance right here, so let's say that that is to be d. Distance d. If you would be multiplying them, so force times distance, this is what we would be calling moment. And if you are to convert this drawing into its respective moment, it would look like this, where the magnitude of this moment right here is equal to F times d. So that is for moment. So when we are to speak about moments, so for example that we are to apply a certain moment about a certain non-static body, for example that you have a certain propeller. So let's say that this is to be a propeller of a certain plane. If you are to apply a certain moment to it, the tendency of this certain body right here is to rotate. So rotate or rotation. And for example that you have a certain beam and it is under static condition. So for example that this is to be your beam. And you are to apply a certain moment to it. So let's say that this is to be a moment. The tendency of this beam right here is to bend in this manner. So in this behavior, what happened in this beam right here was to bend. So bend. And another thing, so for example that you have this cross section right here and you apply a certain moment to it, the tendency of the body is to twist. So in our topic for today, we would be defining moment of inertia as the resistance to rotation, to bending, and to twisting. So that is moment of inertia in a nutshell. So what do we call those moments of inertia that I have defined earlier? So basically, moment of inertia has three major types. So the first type is what we would be calling mass moment of inertia. The second one is what we would be calling the area moment of inertia. And the third one is what we would be calling polar moment of inertia. So for your mass moment of inertia, this is to be the resistance to rotation. And as for area moment of inertia, this is the resistance to bending. And for the polar moment of inertia, this is to be the resistance in twisting. So in statics of rigid bodies, the topics that we would cover here would be that of these two only. So this is for statics. And this is for dynamics. So once again, we would just be covering these two right here. Okay, so let's proceed first with the area moment of inertia. So in this slide right here, area moment of inertia is denoted by the letter I. And it is the resistance to bending and deflection. So for example that you want to check the moment of inertia about this certain axis, so let's say that that is to be letter I, so this is to be inertia, and if you want to get its area moment of inertia about a certain axis x, so that is to be Ix. And the general equation for this is the integral of y squared times the differential area. So what are these terms right here? So your y is the distance from your axis up until the differential area. So that is to be dA and the y squared. But if you are to solve for the inertia about the y-axis, that is to be integral of x squared times differential areas, where your x is to be the distance from your y-axis up until the point that you are analyzing, or your differential area. So that is the general equation for your moments of inertia. So for polar moment of inertia, so for your polar moment of inertia, it is denoted by letter J, and it is just basically the sum of the inertias about the two major axes. So that is to be Ix plus Iy. So it would be as simple as this. Back to the area moment of inertia. So can we solve for the moment of inertia without using the commands of integration? So the short answer to that is yes, you can. So if you are to have these certain basic shapes right here, using this general equation right here, these equations right here was derived if these are to be your sections. But take note, guys, that these formulas right here are only the moments of inertia about their centroid. So for example, that this is to be your Ix, this is to be Iy, and this is to be Ix. This is also to be Ix, this is to be Iy, and whatsoever. These are the respective formulas to it. So once again, these formulas are only applicable to the centroidal axis of these basic shapes right here. So for the rectangle, for the moment of inertia about the x-axis of a rectangle, that is to be base times height cubed, so bh cubed divided by 12. So for triangles, that is to be bh cubed divided by 36. So for circles, that is to be pi r raised to 4 divided by 4, and whatsoever. So if you are to use this equation right here, you would still get the same value if you are to use this equation right here. So there. But like what I have said earlier, that these equations right here are only applicable if you are to get its moment of inertia about the centroidal axis. But what if that, for example, in this figure right here, this x-axis right here is not on the middle? I mean, it's not on the centroid. So this is not the centroidal axis. Can we still use these terms right here? So once again, the short answer to that is yes, but we would be applying a certain formula which we call transfer formula. So the idea behind the transfer formula is that, for example, that you have already solved for the inertia about the centroidal axis, which is here. So this is to be your centroidal axis. Wait. So let's say that this is to be your centroidal axis, and you want to solve for the axis about this axis right here. So what we would be doing is that we would be transferring the moment of inertia about this axis right here to this point right here with the use of transfer formula. So your transfer formula is basically, let's say Ix is equal to your moment of inertia about the centroidal axis is to be Ixo. This is to be your moment of inertia about the centroidal axis. So you can solve for that using these formulas right here, plus the transfer formula itself. So your transfer formula is equal to AD squared. This A right here is equal to the area of the figure, and D squared is equal to the distance from this axis right here, or your centroidal axis, up until the axis of your choice. So for example, so if you are to analyze this, so this is to be your value for D. So this distance right here. So let's have an example later. But first, I would want to make a certain emphasis here. So this is only for your value for Ix. But what if you are to solve for the value for Iy, which is the moment of inertia about the y-axis? So once again, your Ix is to be the resistance of your section to bending about this axis right here. But if you are to get for the value of Iy, that is to be this axis right here. So it would be quite simple. The new base of your y-axis is to be your h, and the new h of your section would be letter B. So from that, your new equation now is to be hb cubed over 12. So that's if you are to solve for the moment of inertia about the y-axis. So basically, I have just rotated this to the point that this was to be my new base and this was to be my new height. But for circles, so whichever the case may be, may it be Iy or Ix, it is still equal to pi r fourth over 4. and as well as for the semicircle. So there, but let's have an example on the transfer formula first. So considering this problem, determine the moment of inertia about x sub 1. So x sub 1 is to be this axis right here, which is located at the top of the vertex of the triangle. So once again, it is located here. So if the base of the triangle is 50 mm and the height of the triangle is 60 mm, well, determine the moment of inertia about x sub 1. So this x sub 0 right here, or x sub O, is the centroidal axis. And if we are to use this equation right here, so for the moment of inertia about the centroidal axis of a triangle, that is to be bh cubed over 36. So IXO bh cubed over 36. So direct substitution. So we have our base already, which is 50 mm, and the height of the triangle is 60 mm. So that is to be 50 mm times 60 mm cubed divided by 36. 36. So the answer here would be, so looking at the calculator to your left, 50 times 60 cubed divided by 36. So the answer here would be 300,000. So 300,000 millimeter raised to fourth. So that is to be for your moment of inertia about the centroidal axis. But the question here is the moment of inertia about x sub 1. And x sub 1 is to be the top of the vertex. So if you can remember our transfer formula here, so to get the moment of inertia about a certain axis, that is to be the moment of inertia about the centroidal axis plus AD squared. So we would now be solving for A and D squared. So for the value for A, so what would be the value of the area of a certain triangle? So the area of a certain triangle is 1/2 base times height. And substituting known values, that is to be 1/2 50 times 60. So our answer here would be, so 50 times 60 divided by 2, that is to be 1,500 mm squared. So that is for A, but what about for D? For D, that is to be this distance right here. So is it given in the problem? So basically it is not, but we can solve for it directly. As you have known already from the previous pre-recorded lecture, that the distance from the apex of a certain triangle to its centroid is equal to 2/3 times height, or whatever this dimension is. So from that, with that being said, I should say this distance right here is equal to 1/3 h. But once again, our value for D should be this distance right here. So that is to be 2/3. So our D right now is equal to 2/3 times H. And our H is equal to, what is it already? So 60. So 2/3 times 60. So I think that is to be 40, if I'm not mistaken. I'm sorry. 2/3 times 60. So that is to be 40. So yes. So 40 mm. So for us to solve for the moment of inertia about this axis right here, so substituting known values, that is to be Ix sub 1 is equal to, so Ix sub 0. So that is to be the centroidal moment of inertia, which is 300,000. So 300,000 mm raised to 4 plus AD squared, and our A and D respectively are 1,540. So plus 1,500 mm squared times 40 mm squared, quantity squared. And from that, our answer here would be, so Ix sub 1 is now equal to 300,000 plus 1,500 times 40 squared, so times 40. So our answer here right now is, so that is to be 2.7 million. So 2.7 mm raised to fourth. So it would be as simple as that.